Hello, everyone, and welcome to the show. My name is Ben, and my guest on the show today is Professor Agustin Valera Medina. Agustin is a professor and a lecturer at Cardiff University School of Engineering and a global leader in ammonia technologies. Agustin has over 11,000 academic citations and is the director of the Centre of Excellence for Ammonia Technologies at Cardiff. Expect to learn why Agustin is betting big on ammonia innovation, the moment that it all clicked when he thought he could really turn ammonia into a clean, green energy source, and the first ammonia projects that Agustin believes will hit the mainstream media first. Ladies and gentlemen, please welcome Professor Agustin Valera Medina. Hi, Agustin. Welcome to the show.
Thank you very much, Ben, for inviting me.
So, I've heard you're very interested in this new fuel called ammonia. Why is ammonia so interesting to you?
Ammonia has become in the last few years, around 10, 15, an interesting vector to decarbonize the industry. And the reason is that it's based on hydrogen and nitrogen, so no carbon added to the molecule, which is a great advantage for, I think, these decarbonization agendas. So now what we are looking at is methods on how we can then use it properly without producing more emissions to the ones that we're trying to abate.
Yeah, so perfect. So it's an energy vector that has no carbon in there. You mentioned that it contains hydrogen. Do you see it as a friend or as a foe to hydrogen as an alternative energy source?
Actually, I see them as a complementary. It's well known that ammonia is the ugly cousin of hydrogen. And I say ugly because sometimes it's just like smelly and it could be toxic in some situations at high values of exposure. But in reality, it's a very benign, useful chemical that has been around for more than 150 years. So if they complement and work together, hydrogen and ammonia can have loads of potential and a solution to many industries.
Oh, brilliant. So you mentioned there about the toxicity. Are there any other complaints or objections that you see the public have? And then how would you answer those complaints? And then how would you present the opportunities that ammonia has to the public?
One of the main detrimentals of using ammonia is that it tends to produce high nitrogen oxides if it's not burned properly. Nitrogen oxides can lead to acid rain, the production of other greenhouse gases, and then the potential of decreasing the efficiency of our systems. So with that, we are trying as part of our research to then minimize the production of these nasty emissions, which is going on pretty well as we are now progressing into the use of different ideas and technologies. Similarly, you have the issue of the nuisance. Ammonia is a smelly gas that you can smell from manure if you go to a farm or close to animals in these locations, which is interesting at the same time because it opens lots of opportunities for rural areas where ammonia can be used. People now aware of the chemical, again, these kind of smells in these particular processes are aware that ammonia is smelly. And as long as it doesn't reach this high level of toxicity we've been talking about, then therefore it's in cities is another story where the smells and the nuisance of ammonia could be a major problem. But there will be some niche applications, some niche areas. And again, as long as we deal with the toxicity, nitrogen oxides, and that nuisance of the smell, I think it will be a way to go in many industries.
Brilliant. So maybe for the people at home listening, could you explain briefly about how those nitrogen oxide emissions could be controlled? Maybe that's something we
Yes.
could talk about.
Absolutely. An interesting thing about these nitrogen oxides is that they're formed by the splitting of the ammonia molecule. So we said we've got hydrogen in them, nitrogen as well. That's what makes this stable molecule. But once that you get into a combustion system, they essentially split up and then form radicals and nitrogen oxides. And nitrogen, finding the oxygen around, just combines and then creates these nitrogen oxides that are just nasty for the environment. So one of the ways actually to then deal with it is using onboard ammonia that can be used from the combustion process itself. Ammonia is a denoxing agent that is used in many applications, including diesel engines, all the catalytic systems that we got for diesel cars. They are fed with AdBlue that contains ammonia. So in the same way, we can use some of this ammonia to denox the atmospheres where we're producing it, essentially killing each other, killing the NOx at the time that we're reducing the onboard ammonia, and therefore producing a very clean atmosphere. That's one of the ways that we are assessing via in clever injection methods, the control of the oxygen intake that we are putting into the system, the temperatures that we are running processes, etc. So there are many different methods of actually tackling the program and this problem using that essential concept.
Amazing. So using it as a denoxing agent, so it almost cures its own problem, which is really interesting. So could you share with me the story about the day or the moment or the time that you realized ammonia could be a future fuel in its own right to help us achieve net zero?
It was an interesting story because we were trying to find a new fuel. Hydrogen was in the agenda of almost every university across Europe, and making a cut was very difficult unless you would have something interesting to offer, like now novel measuring techniques, advanced systems for combustion testing, etc. And one day, 2 days before actually Christmas in 2013, we received some people from Siemens in turbomachinery and energy saying we want to burn ammonia. I remember at the time, it was late that afternoon, everyone in the room was start looking at each other and thinking, why are we going to do this? And eventually I thought, okay, we were looking for something new. Let's give it a go. We started a program from there that lasted around 3, 4 months, initially with some literature review that showed that in previous years, in the decades of the 50s, 60s, actually ammonia had been used very successfully in places like the US, where they tested for replacement of natural gas in army and aerospace applications. But it turns out that because of the oil and gas revolution, ammonia was just put aside and then these fossils took over. But now that we are in the decarbonizing agenda, climate change being one of the objectives of all our research and development, then ammonia has taken again a role in this decarbonization mixture of fuels that we can use. And Japan in 2013-14 started a very impressive program that led to many technologies that we're now evaluating as part of our contribution. So it was at that point, just as we were finishing 2013, ammonia appeared in my scope and my site of different research areas to pursue. And eventually, when we poured it for the first time in our facilities and successfully managed to then produce a flame of consistent temperature that was in the middle of 2014, that's when we realized this has potential.
Amazing. So it's got the potential. It's already coming onto the stage, as it were, in places like Japan, you said. Where are the first ammonia projects that you believe will really start to take mainstream media attention and that it'll be in like the news, as it were?
It's interesting now. We hear and see in many blogs, a lot of newspapers, and also journals that have been addressing the issue of decarbonizing the maritime industry. So, marine systems will be the first, actually, are the first that now are running on ammonia. There's an organization called the Ammonia Energy Association, and they keep track of many of these advancements, and the latest has shown that they are already commissioning around 140, 170 new vessels worldwide running purely on ammonia engines. And this because of the engine manufacturers that are working with them. So what it's going to be the first place of ammonia will be for long distance maritime systems. The second one, I think that is probably going to be even as large, if not even larger, than the maritime industry will be coal power replacement in China, South Korea, and Japan. A few years ago, Japan started a program to decarbonize coal power stations. They are the only G7 members that still run coal and still will be running it because they have that available and is relatively cheap. So one of the main problems, obviously, decarbonizing them and having now this new vector of ammonia, they start some trials that show very nice progress because not only reduce CO2, but also minimize the NOx emissions, the nitrogen oxides we were talking about, using these combined onboard ammonia nitrogen oxides in the furnace. So eventually, it's even better than using coal directly. So because of that, they're moving to replacement of around 30 to 50% coal using ammonia. And now we think that China has been producing and manufacturing and building up all these coal power stations, they say once per week. Then that is going to be a major impact for the use of the chemical. So I think it's these two where we'll see things progressing. And finally, in Europe, where we'll see things as well taking up, is on the front of rural applications. Because as I've said, ammonia has the potential of again being used in these places. Public perception is not that bad; it's actually quite good. And another thing that is interesting is that ammonia, from the 150, 180 years that has been around, has been used mainly as a fertilizer. So if that combines with the fertilizer, the use of power, the potential production of heat using a single molecule, well, it solves many of the current issues that these locations would have. So I think it's these three where we'll see things happen in the next 5, 10 years.
Amazing. Well, that's good news because I imagine the demand for ammonia and then green ammonia will increase as well with all this demand. Really quickly, how much do you expect this demand to increase compared to the current existing fairly mature value chain that it lives in at the moment?
Everything depends on how we progress on the production of ammonia. According to the Hydrogen Council, they see that for hydrogen production in the next 10 years will require around 180 million tons more just to then feed the industry. But then out of that,
Mm.
around 40 will be in other molecules like methanol or ammonia. Now, that's in the next 10 years. But if we're thinking about, again, the maritime industry, then that would require an entire boost of around 3 to 4 times the current production rates of ammonia being produced worldwide, which is again massive.
Wow.
Is around 300 million of tons being produced globally. And with that, again, using conventional methods or the ones that we have been talking about, the green hydrogen recovered from renewable sources. But there's another case that is even more interesting and that poses a fantastic scenario for the near future. And that's that we reach a point where we can reduce the cost of producing hydrogen and ammonia, especially ammonia, using fuel cells or surface reactions that will combine only water with air, and out of that you will get direct ammonia. If that was possible,
Mm.
that will revolutionize the entire energy agenda worldwide. And we will be talking about 3, 4 times, we'll be talking about, again, orders of magnitude higher for the replacement and use of ammonia because it will be cheaper than using fossils, will cleaner, and then it will just comply to any other different method. Actually, it will be the way to distribute hydrogen for many other applications, for example, in cities, as we were saying before.
Amazing. So it's those kind of technology innovations that will enable the ammonia economy to really push on, like you say, to orders of magnitude than it currently is, enable all these amazing use cases. Um, is there any research at the moment that you're involved in that you could share maybe about other innovations that are perhaps going on?
Mhm.
Um, just a bit of time here for you to say some really interesting stuff about ammonia research.
Yeah, absolutely. I mean, we got many that go from small to medium, large size boilers. We got furnaces development. We are looking into internal combustion engines, fed using stratified and clever injection methods. But one that is particularly interesting and very fun on is the one that is related to plasma enhanced combustion. So plasma enhanced is when we have a plasma being produced by this high voltage between two electrodes, and they produce, like in the movies, you see Frankenstein, all these different lightnings happening all around the place. It's just plasmas essentially. But now we're controlling them. And with that, what we do is we split up the ammonia molecule and then produce all these radicals before they actually start the oxidizing or recombination with oxygen process. And when that happens, then that reduces the nitrogen oxide emissions and then improves the combustion profiles, reducing the flame front. So that's very important, especially if you think that eventually we'll need very small systems to then be, I don't know, automotive, heavy duty trucks, or even trains using this molecule. So ammonia plasma enhanced combustion sounds like very interesting, sometimes science fiction type of concept that seems to be working. So yeah, things like that we're doing now these days in our lab.
Yeah, that's really interesting. Where would you put plasma-assisted ammonia combustion on the kind of technology readiness level scale? Where would it sit at the moment?
So we see it happening in, for example, automotive applications, where you can then
Hmm.
produce all these radicals before they get into your combustion chamber, your cylinders. So they're ready
Hmm.
to ignite, and then don't give enough time to then think, am I going to produce nitrogen oxides? No, just go and then produce the radicals and then form the flame or the combustion explosion that will just produce this process. So that's, for example, one that can be assessed directly. A few years ago, Honda and Toyota, they incursion on this idea and gave it a go with, for example, the case of hydrogen using plasmas. There are some patents actually on ammonia enhanced plasma that didn't reach the final system. It was just actually to split it up and then produce the hydrogen. But ours is producing radicals from the ammonia directly and feeding into these units. So I think automotive will be a very good place to start with.
Brilliant. So it's finding the use case for the technology rather than trying to work back the other way. That's really cool. So you mentioned the boilers and the furnaces and how you're almost scaling up to industrial applications from lab scale, let's say. How are you finding that? And as someone who is working in a similar kind of sector alongside with hydrogen and trying to get that into industrial furnaces, where do you see the value in academic research to help industries decarbonize?
I see it as a massive step forward and require part of the bridge to then jump the gap between academia and final commercialization. When we started this furnace development, we initiated with a very small system that was producing around 10 to 20 kilowatts power. In terms of, again, the scale, just to think about it, a single light that we got, light bulb at home, is around 5 watts. So we're talking about, again, your 50 kilowatts. That's around 1,000 bulbs that we can then ignite using this power. Sounds a lot, but with a flame, it's not that much. It's probably the size of what my head would be, somewhere around, I don't know, 30 centimeters long, isn't it? Something like that. But to make the scaling up of an order of magnitude of that power, and not even that, like around 30 times that is now what we are running at these days, so around 1 megawatt, is a massive step forward and
Mm,
requires a lot of engagement with industry, requires a lot of technical issues because having the delivery of the molecule into these furnaces at that scale requires systems that haven't even been designed yet. So that is a lot of novelty, a lot of innovation, and the understanding of what the fundamentals behind all these interactions, something that industry sometimes cannot bring forward or include in developments. They can include how to then deal with these scales. They can include the commercialization. They can add to the design of the piping, delivery systems, etc. But when it comes to then having the final scale-up version of what a burner would do, then you need to then have proper understanding, research being done. Because the way that we tend to do it is you have your small burners, then they show that they're possible to ignite and produce a stable flame. Then eventually you will use that information to feed into some modeling mechanism, some computational fluid dynamics modeling that will give you the hints on how to then scale it up. And then once that you have that hint or those tips from the model, then you can then try build up, manufacture it, and then put it together to then see it working. Because many times the model might not be right. You still need to then test it experimentally. And that, again, in industrial sites is sometimes a no-go or impossible, too expensive,
Mm.
or even too dangerous. So that's the reason, because when it comes to this type of developments, having industrial support is essential, but academic background is a key component to then moving scaling of any of these systems.
Brilliant. Yeah, that's really interesting. So you're taking the lab scale information, applying it to some kind of computational model, which will then inform the scale up at a larger scale, either pilot or commercial scale. Brilliant. Final question on kind of ammonia. You've mentioned the kind of testing, and we'll call it de-risking testing on ammonia fuel. What other things, maybe outside of the furnace or outside of the boiler or outside of the energy system, do you think need to happen to enable ammonia as a technology for the future?
Well, first of all, we need to then have more accessible, cheap systems for our alarms. At the moment, they are again bespoke type of systems to then determine what is the levels of ammonia that we got in surroundings. Uh, One that is critical is, for example, emissions control. I was having a chat recently with the environmental agency, and they are trying to then put together some procedure to determine how to measure nitrogen oxides. This, again, as I said, is one of the detrimental issues of having ammonia technology, is that we're trying to then reduce and then eventually eliminate. But in the time that that happens, they will need, there will be a need to do the proper measurements to determine what is going on in a particular system. So that hasn't been done yet, and that needs to then be developed at an industrial scale. Another one that is critical is the training, because one of the main issues with ammonia is, again, its toxic nature, that if it's not properly addressed, then can then potentially be lethal. And to avoid that happening in industry that has been ongoing for 150 years is just through training, proper training that people dealing with the chemical require. That needs to then be done. We have done it for refrigerants, we have done it for processes, also fertilizers, but never as a fuel. So that just changes the way that things need to be done. Another important aspect is to understand what are the critical impacts that ammonia and its gases will produce in systems that we are currently running with conventional materials that we have used for fossil fuels. We still don't understand that and how that is going to impact. Just to give you an idea, once that we start this process of breaking up the ammonia molecule, as I said, you have the hydrogen, you have the nitrogen. So there are cases where you end up with loss of hydrogen going outside in the flue stack. And when that happens, you have potential a bomb, and that can happen. So how are you going to then burn it down? It's one of the aspects that, when using this technology, needs to be taken into account.
Brilliant. Okay, thank you, Agustin. And finally, what advice would you offer to a younger engineer or a graduate or even a student that you teach on a day-to-day at Cardiff? What advice would you give them, and what would you leave them with at the end of this episode? What would you say to them?
As I said in the story I told about how I found ammonia, I remember again seeing the face of everyone thinking, why are we here? Just we want another project. Why not? I can give it a go. And the head of our department just looked at me. And then once we finished that meeting, went out and said, well, if you want to take this project, fine. But just remember, get not to put a lot of time on it, and think of it as if it was a Cinderella project. That's the way he called it. A fairy tale that eventually will just turn out to be a pumpkin and nothing else. Uh, But I think that the interesting thing was that seeing Japanese and some other institutions already working on this concept, seeing that there was already some track record from previous years, and that the main issue that we're facing is a commercial cost-based issue, uh, made me think, okay, well, it's probably not that. It's just that we haven't found yet the better method to just burn it in a correct way, produce it in a cheap manner that will allow this chemical to be part of our energy mix. So, on those grounds, I never lost the hope and faith of using ammonia for energy purposes. I haven't lost it yet. I have talked to many colleagues over the years, and they say, well, yes, eventually you will just dry out. But I think there will be some niche applications where it will just make the whole difference. And when I talk to many of my students, I say, well, if you believe in a concept and you have seen that there's been some development, you think that there's some way forward and some future, don't listen to those voices saying, well, this will never work or this doesn't have any future. Just believe in that idea, believe in what you can do, and with the expertise that you are getting, all the skills you're learning, and the potential opportunities that will open in the future with artificial intelligence and many other resources, that might become a reality that will change the world. So don't lose faith, keep working on it, and go for your dreams essentially to make them happen. That's my advice to any student that is thinking about crazy thoughts.
That's amazing. Thank you so much, Agustin, for your time. And if people want to keep up to date with you and your research, is there any place where they can keep up to date with that? Or
Yes, absolutely. I mean, they can use our website via Cardiff University at Valera Medina A1 at Cardiff AC UK. Everything is on my profile website. They can see it, and there's also a blog for the Center of Excellence on Ammonia Technologies that they can join and see what we're doing in all our fronts, from the small to the large size systems that we're running these days.
brilliant. Thank you, Agustin. I'll have that all linked in the description of the videos for the people watching and listening. So thank you for your time, and I'll see you soon.
Thank you very much, Ben. See you soon.